Hello everyone and welcome to our calculus notes. Today we're going to be talking about solids with known cross-sections. The disk method relied on using circular cross-sections to find the volume. Now we generalize this process for solids with cross-sections of any other shape with known area formulas. Okay, so let's check out this demonstration on Wolfram Alpha. Okay, so we can take any two functions or the region bounded by the two functions, and we can take cross sections that are perpendicular to the x-axis here of any known shape that we know the area formula of. So for instance, we can take squares. So we would just take the distance from here down to here and then make a square out of it by coming straight up off the page. Okay, and you can see that's what's happening over here with this solid. So right across here, they just made a square. Okay, and you can do that across the entire function, and you get a solid that looks something like this. Now, because we know the area formula for a square, we could actually find the volume of this shape. Pretty crazy, huh? Now, our cross sections could also be equilateral triangles because we know the area formula for an equilateral triangle. Okay, so you can see there, we would just take this length, the distance between the two curves, which we already know how to find, and then take it and make an equilateral triangle out of it. Can also do this with semicircles, okay, because that would just be half of a circle. And rectangles would also work, and you can see the shape that would be formed here. And this will work for any base region. Okay, so we can have these two functions right here, and then we can put rectangles perpendicular to the x-axis, and we would get this shape, and we could find this shape's volume. No problem with calculus. Make those into equilateral triangles. So lots of interesting things that we can take a look at here. So here are our formulas for volumes of solids with known cross-sections. Number one, for cross-sections of area, capital A of x, taken perpendicular to the x-axis. The volume is going to be the definite integral from A to B of the area of the cross-section with respect to x. Okay, so where are these things on here? Well, here is x equals a. You can see down here on the x-axis. And then here's x equals b. Okay, and so you can see our base region would be right down there. And then our cross sections are going to be this shape right here. Okay, and this is where you find your A of x. So it's the area of that cross section, and this is going to be a formula. So you have to know the formula of that cross section. So basically what we're doing is we're taking a width here, and when we have our area, we can multiply it by the width of delta x, and then we get a volume for that little slice. And by integrating this from A to B, we're actually getting all of the little slices that we can get all the way across this figure. Okay, so we're just slicing it up. So some things to note. When this is perpendicular to the x-axis, notice our area formula will be a formula of x with respect to x, and then A and B are going to be on the x-axis. So the same process for number 2. For cross-sections of area A of y taken perpendicular to the y-axis, the volume here is the definite integral from c to d of A of y with respect to y. Okay, so now c becomes a y value. So it would go from here all the way up to here. So that's the length that we're taking our cross-sections of. Notice we still have the same base shape here, But now our cross sections are taken perpendicular to the y-axis. Okay, and so A of y now becomes the area of this shape right here. And then the width of these cross sections is now delta y. So you can see we're getting little shapes right here. And then we get a volume for that little slice. If we took all the cross sections here, we could actually find the volume here of this entire figure. Now, in looking at these two drawings, if we wanted to find the volume here, in my opinion, it would be tough to find a formula for a of x because you can see that it's curved right here. Now, finding a of y would be a little bit easier because this is just a square. So if we know the base down here, then we also know the area of the square. So those are going to be the tricks that we have to look at when finding volumes of solids with known cross sections. Okay, so in our first example it says find the volume of the solid shown in the figure. The base of the solid is the region bound by the lines f of x equals 1 minus x over 2 and g of x, which is negative 1 plus x over 2, and the line x equals 0. The cross sections perpendicular to the x-axis are equilateral triangles. Okay, so let's figure out what's going on here. Here is the function 1 minus x over 2. So this one is f of x. This function here is negative 1 plus x over 2. So here's g of x. And then here's the line x equals 0. Okay, so here is the base of our solid. And I like to draw my representative rectangle on this base because this is going to end up being part of our formula. So this is actually the base of that equilateral triangle. And what we're looking at here is the top view. Up here is our 3D view. And you can see the base that we just drew is down here. And notice the axes get kind of funny. Here's our x-axis and the y-axis, so it swings around just so we can look at this. And here you can see f of x and g of x that match up with our top view. Now the little representative rectangle that we drew is right down here, and above it you can see our equilateral triangle coming up off of that representative rectangle. So the face of this equilateral triangle is our capital A of x. So when we set up these problems, the first thing we want to do is find a formula for the area of our known cross sections. Okay, so in this case we want to know the area of an equilateral triangle. Okay, and you don't have to really memorize this. You can just reference the formulas in the back of your book, but it's going to be the square root of 3 over 4 times base squared. And that base we're talking about is the base of the equilateral triangle, which you can see right here. Basically, it's going to be the height of this representative rectangle. So we need to find the height of this representative rectangle, which I'm just going to label as base. And it's going to be the upper function, f of x, minus the lower function, g of x. And we'll just substitute our functions in now. So f of x was 1 minus x over 2. And then g of x was negative 1 plus x over 2. And we're going to add the opposite here. So we get 1 minus x over 2 plus 1 minus x over 2. And this is going to equal 2 minus x. Okay, so there is the formula for our base. So now if we're trying to find a of x, so the area of the equilateral triangle right here in terms of x, well, it's going to be the equilateral triangle, the square root of 3 over 4, times the base, which is 2 minus x, and squared. Okay, so really two things you have to do there. One, come up with your general equation for your cross-section, and then figure out how to write that as a function of x by looking at the functions that you're given. So now finding volume, it's going to be the definite integral from a to b of the area of our known cross-section with respect to x. Okay, so a to b, where is this going from? Well, it looks like we're going from 0 up to where they intersect here at 2. So if you're looking at the top view, that's what you're looking at. If you're looking at the 3D view, it's going to be this along this path right here. So from 0 to 2. So it's the definite integral from 0 to 2 of our function, square root of 3 over 4 times 2 minus x squared with respect to x. And when we evaluate this in our calculator, we get about 1.155 units cubed. All right, let's move on. So in this example, it says find the volume of the solid shown in the figure. Well, it's not actually shown. We're going to practice drawing this here so that we can understand this a little more deeply. The base of the solid is the region bounded by the functions f of x equals 3x plus 3, and g of x equals negative 3x plus 3, and y equals 0. And the cross sections are perpendicular to the y-axis, and they are squares. All right, so let's graph the top view of this before we try the three-dimensional. So we have the function f of x equals 3x plus 3. So here's plus 3. And we have a slope of 3. So that's going to meet down here. So here's f of x. And then g of x is negative 3x plus 3. So now we just have a negative slope. It's going to go this way. Here's g of x. And the line y equals 0 right across the bottom there. So that is going to be the area of our base. Now it says the cross sections are perpendicular to the y-axis. So what that means is my representative rectangle is going across this way. Now let's go ahead and put this on a three-dimensional graph. So we'll label this as the x-axis and this is the y. And so we know our functions start at y equals 3. So we'll just go 1, 2, 3. And then they both intersect at negative 1 and 1. So we'll draw these here. And then there's the line y equals 0. Okay, so we just took that base and laid it down flat. And now the cross sections are squares. So basically, we need to take this length and make a square out of it. Okay, and we know it's a square because it's perpendicular here, and these lengths are the same. And we can make those squares going across the entire section there. And so I'm going to draw in my representative rectangle that we drew down below. So that was right about here. So I'm going to take this length and make a square out of it. So we go up the same distance. Okay, and so here's our little cross section, three-dimensional view here. And what we need to find now is the area of one of these faces. And we need to find this in terms of y, because the cross sections are perpendicular to the y-axis. So we need to find the area of a square. And what that is, it's going to be the base squared. Okay, and what is our base? Well, before, remember our base, basically it's going to be the height of this representative rectangle. So our base is right here. Now, because these are horizontal rectangles, we need not f of x, but we need f of y. So we really need to change all of these into functions of y. Okay, so for this one we had y equals 3x plus 3, and we need to solve for x. So notice we would subtract 3 and divide by 3, so we really have y minus 3 over 3, and that is f of y. And then for g of x, we have y equals negative 3x plus 3. And if we solve for x, we would subtract 3 and then divide by negative 3. So we get y minus 3 over negative 3. And that equals g of y. And so our base is going to be g of y minus f of y. Okay, so g of y was y minus 3 over negative 3, and then minus f of y, which is y minus 3 over 3. And here, if we change this sign, we could actually just change the denominator to be negative 3. And now we can see we have common denominators, so we can actually add these together. So the base is actually 2y minus 6 over negative 3. Okay, so if we want to find the area of our known cross-section with respect to y, all we have to do is substitute base in for base squared. So we get 2y minus 6 over negative 3 squared. And then finding the volume, we want to take the definite integral. Well, from where? Well, now we need y values. So where are y values going from? So if we're taking these rectangles, we're going to take them from here all the way up to here. So we're going from y equals 0 up to y equals 3. Okay, so the volume is the definite integral from 0 to 3 of a of y, which is 2y minus 6 over negative 3 squared, with respect to y. And when we evaluate this, we actually get a volume of 4 cubic units. Alright, so the process was the same. The only thing different here was that we needed to find a function of y for our area because the cross sections were perpendicular to the y-axis. Alright, let's move on. So in this example it says find the volume of the solid shown in the figure, and the base of the solid is the region bounded by the lines sine of 2x plus 2, which you can see right here. Okay, and negative sine 2x minus 2, which is right here. Also 0 is right here, and then up to 2 pi. So for letter A, it says the cross sections perpendicular to the x-axis are isosceles right triangles. So here is that isosceles right triangle. And if we think about an isosceles right triangle, I'm just going to draw it here. Basically, this becomes the right part. This is the isosceles part. Now we know the area of any triangle is 1/2 base times height. Okay, so if we look at this, the base is right here, and basically that's the distance between our two functions on the bottom, and over here it's going to be that representative rectangle. So this is the base right here. So finding the base isn't too bad. It's just going to be f of x minus g of x. which is just going to be sine of 2x plus 2 minus negative sine of 2x minus 2. And we'll change our signs here. And so we get 2 sine of 2x plus 4. And this is the base. Okay, so we have one part of our function, a of x, but now we also have the height. So let's deal with the height over here. And the height is going to be the distance from here to here perpendicular. Now, thinking back to geometry, if we draw the altitude of that isosceles right triangle, we know we split this right here. And the height is also going to equal half of the base. So when you split an isosceles right triangle with its altitude, you create another isosceles right triangle here. So we know that height is going to equal 1/2 of the base. Okay, which is good because we know what the base is. So let's rewrite this. We have 1/2 times the base times the height, which is 1/2 base. So if you have 1/2 base times 1/2 base, you really have 1/2 base squared. Okay, so all in all, our area of our known cross section of x is going to be 1/2 times the base, which is 2 sine 2x plus 4, and then that squared. And if we clean this up a little bit, we'll distribute the 1/2 in here. So we really have sine of 2x plus 2 squared. And that's the area of this face right here. Now to find our volume, we just need to find our limits of integration. Okay, we're going to find these right up here. So we're going from 0 all the way up to 2 pi. Okay, right along here. So definite integral from 0 to 2 pi of capital A of x. So sine of 2x plus 2 squared with respect to x. And using our calculator here, we get 28.27 cubic units. So this is the amazing power of calculus. You were just able to find the volume of this shape right there. Pretty unbelievable. Anyway, I want you to go ahead and give letter B a try on your own. Go ahead and pause the video and then come on back when you're done to check your work. Since the cross sections are semicircles, basically the area of a semicircle is pi r squared over 2. And so our goal now is just to find that value of r. And so if we look over here, We knew the entire base of this is the diameter of the circle. And we already determined that that was 2 sine 2x plus 4. And so if we want just the radius, all we have to do is cut this in half, and so we get sine 2x plus 2. So now that we know the radius is sine 2x plus 2, we simply substitute this in right here. And so the area of our semicircle, our known cross-section, is going to be pi times sine 2x plus 2 squared over 2. When we find the volume, we're just going to integrate this from 0 to 2 pi. So it's the same limits of integration. And just one note here, that I took the constant pi over 2 and just put it on the outside. So it's still a good technique, makes it a little easier there. And when we evaluate this, we get 44.413 cubic units. Alright, so that has been finding volumes of solids with known cross sections. Thanks for watching.